time domain analysis. So what do you mean by time domain analysis? Can anyone tell me what do you mean by time domain analysis actually? Yes, study of how response changes with respect to time, system behavior with respect to time. Checking of system behavior with respect to time, right? System behavior. So time domain analysis, right? It is the analysis of system's response with respect to time, right? Analysis of system's response with respect to time, right? You can write down the definition if you want, but that is not so important definition. That is not very much required, but still, see what is time domain analysis, right? Analysis of system's response with respect to time is called as time domain analysis, right? How the system responds with input, yes, right? So it is the analysis of system's response with respect to time. That is what is called as time domain analysis. Is it clear, right? So let us say you have two different cars, right? One is ambassador, right? In olden days we used to have ambassador cars, like, right? So one is your ambassador car, which is something like this, right? The other car is some Lamborghini or else Jaguar, something else like that. So both of these cars have their own specifications, yes or no? Both of these cars have their own specifications, right? One specification is, let us say, this car reaches 100 kilometers per hour. This car reaches 100 kilometers per hour speed within some 20 seconds. Whereas this car requires at least 20 minutes to reach 100 kilometers per hour. So this requires only 20 seconds to reach 100 kilometers per hour. This requires 20 minutes to reach 100 kilometers per hour, right? So if money is not a constraint, which car will you prefer? If money is not a constraint, you will prefer this particular car because it is faster, right? Because this car is faster. This is a faster one, right? Whereas this car is slower. So let us say you have two ceiling fans. You went to a store to buy two ceiling fans, buy a single ceiling fan. There he has shown you two different ceiling fans, right? So one ceiling fan is like, if you set its speed at 5 and turn it on, right, it will take 20 minutes to reach its full speed. And there is one more ceiling fan that he has shown you, that is, after switching on, it will just take 10 seconds to rotate at full speed, right? Which ceiling fan will you prefer? This is fan 1 and this is fan 2. This one only, right? So after switching on, in order to enjoy full speed, you have to wait in the room for 20 minutes. What is the use, right? You have to wait in the room for 20 minutes. In some places, the difficulty is, right, the electricity supply will not be there for 20 minutes continuously. There are places like that in India, right? So if it cannot reach full speed within 20 minutes, you cannot enjoy its full speed, right? So if it reaches its response faster, then it is preferable, right? System which reaches its output faster is preferable, right? Yes or no, right? So from these examples, what you can conclude is system which reaches its output faster is preferable, right? Such systems are preferred, yes or no? Faster systems are preferred, right? So how did we know this fan reaches in 10 seconds and this fan reaches in 20 minutes? How did we know that this car reaches in 20 minutes and this car reaches in 20 seconds? So we have carried out analysis on these systems. So in time domain analysis, we are going to do the same, right? We are going to carry out analysis on the systems, and we are going to see the figures of merit, right? Every system has certain figures of merit, right? This system has figures of merit, right? Like the settling time, rise time, delay time, time constant, all these things. All these are what? All these are figures of merit. Figures of merit. So, how did you say that this is better than this? Right? It has a figure of merit. What is this? This 20 seconds is the figure of merit. How did you say that this span is better than this? It has a figure of merit, right? Its settling time is 10 seconds, whereas its settling time is 20 minutes. Its settling time is 20 seconds, whereas its settling time is 20 minutes, right? So all these figures of merit you have to calculate using analysis on the systems, right? So that analysis is what we are going to carry out in time domain analysis. Is it clear? Right? So that particular analysis is what we are going to carry out on various systems, on different systems in this chapter, right? So what are those different systems? We have to generalize systems into a particular category, and we will calculate the figures of merit for each and every type of system. Is it fine? We have seen various transfer functions, right? So many transfer functions. Let us say some transfer function T of S, right? So every transfer function we have seen till now, they are ratios of two polynomials in numerator, one polynomial on numerator and another polynomial on denominator. Yes or no? Right? All the transfer functions which we have seen till now are ratios of two polynomials in the numerator and denominator, right? So there is a numerator polynomial. Let us say it is b0 s power m, b1 s power m minus 1 plus b2 s power m minus 2, so on, bm minus 1 s power, sorry, this is bm only, bm s power 0, right? So this is the general form of a polynomial in terms of s, right? So let us take another polynomial in the denominator, a0 s power n plus a1 s power n minus 1, a2 s power n minus 2 plus so on, an s power 0, right? So we have two different polynomials, one on the numerator and one on the denominator, right? So the polynomial in the denominator is called as characteristic equation of our system, right? This is the transfer function of our system, and the polynomial in the denominator is called as what? This is called as characteristic equation of the system. Characteristic equation of, right? So why is it called as characteristic equation is the roots of this polynomial are going to decide the behavior of the system's response. Response means output of the system, right? So if you are giving some input, the system is responding by giving its appropriate output, right? So the system's response is depending on what? That is depending upon the roots of this polynomial. That is the reason why this is called as this polynomial made equal to 0. When this is equated to 0, that is an equation, right? When this is equated to 0, then this is an equation. That equation is called as this particular equation is called as what? Characteristic equation, right? So this T of S, you can write this T of S as ratio of two polynomials. One polynomial is a function of S, numerator polynomial of S upon denominator polynomial of S, right? So denominator polynomial of S made is equal to 0. This is what is called as what? Characteristic equation. Denominator polynomial of S made equal to 0 is called as characteristic, right? So d of S made is equal to 0 is called as characteristic equation, right? Therefore this T of S is equal to n of S upon d of S. This can be simplified in another form also. We can write this thing in another form also, right? So how can we write it? We can find out the roots of the numerator and we can find out the roots of denominator, and we can write it in factorized form, right? So let us say s plus Z1, S plus Z2, S plus Z3, so on, S plus Zm. Right? I have factorized the numerator, and there might be some constant term here, some k term here, right? Now I am factorizing the denominator, right? So numerator or denominator, whatever it might have roots at any place, right? So let us first of all consider it as S plus P1, S plus P2, S plus P3, so on are the roots of the denominator, right? So there can be, this Z1 can be 0 also, this Z2 can be 0 also, right? If Z1 is 0, what will this expression reduce into? S plus 0, that is equal to what? Simply S, right? So you can write this equation as Ks into S plus Z2, S plus Z3, S plus Z4, so on, right? So there can be poles also in the denominator. There can be zeros also in the denominator here, right? This can be S plus 0 also. If this is 0, you can write it as S, right? So this can be written, right? S plus Z1 or else S plus P1. P1 can be 0, P2 can be 0. Any number of zeros can be there in these constants, in the place of these constants. Therefore, let us say there are such roots, right? So I am calling it as S power R, S plus P1, S plus P2, S plus P3, so on, S plus Pn minus R, right? N is the degree of the denominator, right? The roots of the characteristic equation or else the roots of the numerator polynomial can be at origin also, and that is the reason why I have considered some roots like this, right? So numerator can have more roots at origin as well as denominator also can have more roots at origin, right? So here one more thing you need to know about is this particular form is called as pole zero form. This form is called as pole zero representation. Pole zero representation, right? Why is it called as pole zero representation? See, why is it called as pole zero representation? See here. Here, the roots of numerator polynomial are what? Minus Z1, minus Z2, minus Z3, minus Z4, so on. The roots of denominator polynomial are what? Minus P1, minus P2, minus P3, minus P4, right? Roots of numerator polynomial are these, and roots of denominator polynomial are these roots, right? So the roots of numerator polynomial, if I put z is equal to 1, what is the value of transfer function? Tell me. Sorry, if I put s is equal to minus z1 here, if I put s is equal to minus z1 here, what is the value of transfer function? Infinity, right? So that is the reason why the values of s which make the transfer function 0, they are given a name called zeros of the transfer function, right? They are given a name called zeros of the transfer function. The values of s which make the transfer function to be infinite, the values of s which make the transfer function to be infinite, they are given a name called poles of the transfer function. Poles of the transfer function, right? So that is the reason why this particular form, this form indicates poles as well as zeros. This form indicates poles as well as zeros. That is the reason why we call it as pole zero form of our transfer function. So any transfer function can be represented in this way also, right? Is it clear? Is it clear, everyone? So now see here, what is the order of the numerator polynomial? What is the order of the numerator polynomial? M, right? What is the order of denominator polynomial? N, right? So denominator, the roots of denominator are deciding the behavior of the system, right? So write down the response. Roots of the characteristic equation are deciding the nature of the response, right? So that is the reason why the order of the denominator is called as order of the transfer function. Highest order of the denominator of the transfer function is called as order of the system. Is it clear? So what is the order of the system here? Here the order of the system is n, right? In this case, order of the system is what? Order is equal to n, right? Highest order of the denominator of the transfer function is called as order of the system. Is it clear? So can I erase the upper part? Yes or no? Can I erase the upper part? See, there can be poles in your system and zeros in your system residing at zero origin, right? So S is a complex number, right? So as S is a complex number, you will have S plane, right? S plane, right? In S plane, you have imaginary part of S and real part of S on the two axes like this. Imaginary part and real part of S, right? So as S is complex number, you are adding Z1 to S, Z2 to S, P1 to S, P2 to, all these numbers are complex numbers, right? So all these are what? Complex numbers only, right? So all these are lying in which plane? Complex plane, right? So these zeros, poles and all these are lying in what plane? Right? So in the complex plane, there can be any number of poles at origin as well as there can be any number of zeros at the origin. There can be poles at the origin as well as zeros at the origin also. This is origin. This is your origin. There can be poles and zeros at origin also, right? So therefore the number of poles at origin is called as type of the system. Please note down type number of the system. Type number of the system is defined as the number of poles at the origin. What is type number? Type number is the number of poles at the origin, right? Type number of the system. Is it clear? So from this transfer function, can you tell me what is the type number of the system? From this transfer function, please tell me what is the type number of this particular system? What is the type number? R, right? So for this particular system, the type number is what? Is R, right? So order of the system indicates, order of the system indicates total number of poles. Order of the system indicates the number of energy storing elements in the system, right? Number of energy storing elements, you can also call them as number of energy storing elements. You can also call them as number of dynamic elements. Number of dynamic elements. What do you mean by dynamic elements? Dynamic elements means the elements like capacitor, inductor, right? Your mass block, spring, all these are called as what? Dynamic elements, not spring, right? So all these are called as what? Dynamic elements. Dynamic elements means their behavior is governed by differential equations, right? So their behavior is governed by what? Their behavior is governed by differential equations. Therefore, what is order? Order is the total number of poles of any system, right? So what does order indicate? Order indicates the number of energy storing elements. What about type? Type is the number of poles at origin, right? The number of poles lying at origin is called. So this transfer function, you can simplify this in another form also. So see here, this is your particular system, right? So T of S is equal to, you can write this particular thing as, take Z1 common, Z2 common, Z3 common, Zm, so on. Take all these constants to be common out of these factors, right? So you will get K into Z1, Z2, Z3, so on, divided by P1, So take all these factors common, P1, P2, P3, P4 out of these, right? P1, P2, P3, so on, right? So what about the numerator now? The numerator is S by Z1 plus 1 multiplied by S by Z2 plus 1, S by Z3 plus 1, S by Z4 plus 1, so on, right? So K is what? What is K? So what is this? It is the numerator had become S by Z1 plus 1, S by Z2 plus 1, so on, right? So next, what about the denominator? The denominator had become S by P1 plus 1, S by P2 plus 1, S by P3 plus 1, right? This is the denominator. Therefore, T of S can be written as like this. We can write T of S to be like this. Can I erase this part? Therefore, T of S is equal to K into Z1, Z2, Z3, K into P1, P2, P3. I can consider it as a single constant, right? So, yes, thanks for reminding. S power R, I forgot to write S power R. S power R also, right? So K into Z1, Z2, Z3 upon P1, P2, P3, right? So we can write this as some other constant KDC. I will tell you why this constant is called as KDC, right? We can write this as KDC, right? So all these constants multiplication, we can write it as a single constant, right? This multiplied by STA plus 1, STB plus 1, STC plus 1, so on, divided by S power R, ST1 plus 1, ST2 plus 1, ST3 plus 1. So this is what we will be going to see, right? So any transfer function can be generalized like this: KDC STA plus 1, STB plus 1, STC plus 1 upon S power R into ST1 plus 1, ST2 plus 1, ST3 plus 1, right? So as the denominator is deciding the nature of the response, therefore this T1, T2, T3, so on, Tn minus R, all these T, these are called as what? These are called as time constants of the system. Time constants, all these are called as the time constants of your system, right? So these are called as what? Time constants of the system, and this particular form of your system is called as, this particular thing is called as time constant form, time constant representation, right? This is called as what? Time constant representation. So this is the general way of representing any particular system, right? This is the general way of representing any particular system. So this is the general way of representing any transfer function, right? So general form of any transfer function is this, that is the time constant form. So in this way we can represent our transfer function, right? So why did we call this KDC as DC gain? This constant as DC gain, why did we call it? So first of all, take down the definition for DC gain. You should be knowing what is DC gain, right? So the DC gain definition, take down the definition for DC gain. It is the gain offered by the system for DC inputs. It is gain offered by the system for DC inputs. What is DC gain? DC gain is the gain offered by the system for DC inputs, right? So let us take, let the type number of the system, is equal to 1, is equal to 0. Let type number of the system is equal to 0, right? So what should be the frequency for a DC signal? All of you respond. What is the frequency for a DC signal? What should be the value of frequency for DC signal? Frequency is 0 for DC, right? Therefore, you can consider this as frequency of DC input is equal to 0, which means what is frequency here? Frequency here is S, yes or no? Which means S is equal to 0, which means S is equal to 0, right? So for a type 0 system, which means this R is 0, for a type 0 system in which R is 0, right? Put S is equal to 0. Put S is equal to 0 in this transfer function. Limit S approaches 0, T of S. Tell me, put S is equal to 0 in this transfer function and tell me. Limit S approaches 0, T of S is equal to how much? See, this is 0, 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 this is 1. 1 multiplied by 0 plus 1, 1. Multiplied by 1, multiplied by 1, multiplied by, right? So this entire thing is equal to what? Is equal to 1. This entire thing is equal to 1. Only thing that is left is KDC. Therefore, limit S approaches 0, T of S is equal to what? It is equivalent to KDC, right? So, if at all you need to calculate DC gain of any transfer function, so if you need to calculate DC gain of any transfer function, just simply put S is equal to 0, that is frequency is equal to 0 in its transfer function. That's it, right? So take down this point also, right? To calculate DC gain in any transfer function, put S is equal to 0 in the transfer function itself. Therefore, in the time constant form, if you put S is equal to 0 in the transfer function, the DC gain is how much? That is KDC. That is the reason why this KDC indicates the DC gain of your system if it is a type 0 transfer function, right? This KDC indicates what? KDC indicates the DC gain of your transfer function if the type of the system is 0, right? Is it clear, everyone? So now we have generalized our transfer function, right? So we have generalized our transfer function as per the requirement. So now one thing we can see is, right? So if the order of the transfer function or order of the denominator is more than order of numerator, right? So T of S is equal to, we have T of S is equal to a numerator polynomial of S upon denominator polynomial of S, right? So let order of numerator polynomial of S is equal to M, let us say, and let order of denominator polynomial of S is equal to N. So see here, order of numerator polynomial is M and order of denominator polynomial is N, right? Is it clear, Shivani Sharma, or else still any doubt? So if M is greater than N, then such a system is called as strictly proper transfer function. Strictly proper transfer function, right? If M is greater than N, it is strictly proper transfer function. If M is less than N, then it is, M is greater than or equal to N. M is greater than or equal to N, then it is called as proper transfer function, right? For the system to be strictly proper, M should be greater than N. M must be greater than N, right? So if M is equal to N, then it is called as proper transfer function. Greater than or is equal to N, it is proper transfer function. If M is less than N, then it is called as improper transfer function. This is called as what? Improper transfer function. Then it will be called as improper transfer function. So this is called as strictly proper. This is proper. and this is improper, right? So all the practical systems are strictly proper or proper only, right? All the practical systems are either strictly proper or proper, right? So systems which have numerator degree more than denominator degree, then those systems are called as improper systems, and practical systems will not be there as such, right? Your practical systems will not be improper systems. Practical systems will be always proper systems only. So let us say you are giving some input. You are giving some input to your system. This is your system, right? Your system has some transfer function. System has some transfer function T of S. So you are feeding some input and you are getting some output C of S. You are feeding R of S as input. So what about time domain? In time domain, it is R of T. In time domain, the output is C of T, right? In time domain, the output is C of T, right? So if you want to find out C of T, how can you find out C of T? First you have to find out C of S. What is C of S? C of T is equal to Laplace inverse of C of S. C of T is equal to Laplace inverse of C of S. So what is C of S? C of S is equal to Laplace inverse of C of S is equal to what? R of S multiplied by T of S. Laplace inverse of R of S multiplied by T of S is nothing but your C of T. So whenever you are asked to calculate the output of any particular system for a specific input, so how will you calculate? You will calculate with the aid of this particular thing. C of T is equal to Laplace inverse of C of S. You will find out C of S and you will find out the Laplace inverse of C of S. That is equal to Laplace inverse of R of S into T of S. Is it clear till now? So let us say C of T is the time response of your fan, your ceiling fan or something, right? So if I switch on the fan now, if I turn on the fan just now, and the maximum speed of your fan is given to be 1000 rpm. Let us say 1000 rpm is the maximum speed that your fan can provide, right? I've switched on your fan just now itself, right? So does that fan reach 1000 rpm immediately? If I turn on the fan, C of T is the response of your fan, I'm saying, right? So 1000 rpm is the final value of your fan speed, right? It will take time. Yes, very good. 1000 rpm is the final speed of your fan. So if I turn on, what happens is the fan starts at 0 speed, slowly it increases its speed, slowly it will reach its final speed. After reaching its final speed, it will stay back at its final speed like this, right? So this is how the speed of fan increases with time, right? So transient state, then S state. Yes, steady state. Transient state, then steady state, right? So with a steady speed, the fan is now rotating like this, right? So after some time, if I turn off the fan, if I turn off the switch, will the speed of the fan become 0 immediately? Tell me, if I turn off the switch of the fan, after some time, at this instant, will the speed of the fan become 0 immediately? Speed again drop very slowly only, right? So this is called as what? This transition is called as transient response. This transition is called as transient response. Transient response means response during the transit from initial state to final state, right? Whereas in this case also you can call it as what? This is transient response, right? So here see this This is constant for a continuous period of time like this. This is being constant continuously. So this is called as steady state response. What is this called as? So our response C of t is a culmination of more than one response. So there is a correction, please note it down. Did I write m greater than n or else n greater than m? So please correct it. That was a mistake. I'm sorry. So it should not be m greater than n. It should be n greater than m. N greater than m for the system to be strictly proper. N should be greater than m. N should be greater than or equals m. If n is greater than or equals m, then you can call it as proper. If n is less than m, then it is improper. The number of poles must be greater than number of zeros, right? So for a system to be strictly proper, number of poles must be greater than number of zeros, right? So any system's response is a culmination of what? It is a culmination of more than one response. What are those responses? Transient response and steady state response, right? So you can write C of t, the response of any particular system, C of t is a culmination of what? It is a combination of transient response, C transient of t plus C steady state of t. Steady state response, this is the response, right? So we have to carry out two analysis. One is transient state analysis, transient response analysis, and the other is steady state response analysis, right? So we have to carry out two analysis, transient response analysis as well as steady state response analysis. Is it clear? So just take down an example how you will find out the response of any particular system. How to find out the response of any particular system. So let us say we have a system, right? Take down this question. Find out the response of the system for unit step input, right? So for unit step input. So what is happening here? This is the system we have. The system we have is 1 by s plus 2, right? So unit step input is given to it. U of t is given to it. Then you have to find out C of t. What is C of t? You have to find out C of t, right? So how you will find out? C of t is equal to what? Solution we are doing, right? C of t is equal to what? C of t is equal to Laplace inverse of. How will you find out C of s? R of t is equal to U of t. Then R of s is equal to what? Then R of s becomes equal to what? If R of t is equal to U of t, R of s is equal to what? R of s is nothing but Laplace transformation of R of t. R of s is 1 by s, very good. So if R of s is equal to 1 by s, we have to find out C of s. So C of s is equal to what? C of s is equal to R of s multiplied by the transfer function of the system, that is T of s, right? R of s multiplied by T of s, that is equal to 1 by s multiplied by 1 by s plus 2, right? So C of s is equal to what? C of s is equal to 1 by s into s plus 2. So you have to find out C of t from this. C of t is equal to Laplace inverse of C of s, that is equal to Laplace inverse of 1 by s into s plus 2, right? Laplace inverse of 1 by s into s plus 2. So how will you find out the Laplace inverse of 1 by s into s plus 2? You have to know partial fractions, yes or no? Do you people know partial fractions or not? 1 by s into s plus 2. Yes, right? So how can you write 1 by s into s plus 2 using partial fractions? Using partial fractions, you will split this. You will split this as a by s plus b by s plus 2. You will split this as a by s and b by s plus 2. You have to find out the values of the constants a and b. What you should do, you have to find out the values of the constants a and b, right? So what are the values of a and b you are getting? Tell me the values of a and b. A is 1 by 2 and b is minus 1 by 2. See, if at all you are taking more time to calculate a and b values, if it is taking more time to you to calculate a and b values, so how you will calculate a and b is C. In order to calculate a is equal to limit s approaches 0, s into 1 by s into s plus 2. So if you put limit s approaches 0, you will get what? You will get 1 by 2. So similarly, you can calculate the value of b. In a similar manner, you can calculate the value of b. Limit s approaches minus 2 in this case, right? The root of this thing you should take in order to calculate b, because b is the coefficient of this, right? Limit s approaches minus 2, s plus 2 into 1 by s into s plus 2. So s plus 2 gets cancelled. In the place of b, in the place of s, if you put minus 2, what will you get? You will get this as minus 1 by 2. So in this way you can simply calculate a and b. So after calculating a and b, this 1 by s into s plus 2 can be further reduced into what? 1 by 2s minus 1 by 2 into s plus 2. So take this 1 by 2 common. 1 by 2 into 1 by s minus 1 by s plus 2, right? So this is what you are getting. If you obtain the Laplace inverse of this, if you obtain the Laplace inverse for this, what will you get? The Laplace inverse for this is equal to 1 by 2. Laplace inverse of 1 by s is 1 minus e power minus 2t. So this is the Laplace inverse of this. Therefore C of t is equal to what? C of t is equal to 1 by 2 into 1 minus e power minus 2t. 1 by 2 into 1 minus e power minus 2t. Since systems are always causal and Laplace is unidirectional. Yes, very good, right? So you have given the input unit step, right? So unit step input is activated at what time? At what time the unit step input will be activated? You are giving the input at what time? At t is equal to, right? Input is given at t is equal to 0. If input is given at t is equal to 0, then can the output be present before t is equal to 0? No, right? You cannot get the output before t is equal to 0. But if you look at this profile, if you plot this graph, if you plot the graph of this, what you will get is, I'll show you here. Not only at t is equal to 0, this is present even before t is equal to 0. Even before t is equal to 0, its value is present, right? So that is the reason why if we are giving input at t is equal to 0, the output must be present only after t is equal to 0, right? So the output should be present only after t is equal to 0 means how will you represent that? You will multiply this output with u of t, that's it, right? C of t is equal to 1 by 2 into 1 minus e power minus 2t multiplied by u of t. This is the output of your particular system, right? So if you do not multiply with u of t, this will be present before t is equal to 0 also, right? The same way, I will give you a problem. Will you find out the response of that? So take this problem. The unit step response of the system with transfer function g of s is given by which of the following waveforms, right? So first of all, you just obtain the mathematical expression. Then from the mathematical expression, you can easily get down the waveform. You can easily get the waveform, right? So just find out the mathematical expression for that. The unit step response of the system with transfer function g of s is equal to 1 minus 2s by 1 plus s, right? unit step response of 1 minus 2s by 1 plus s is asked. C of t is equal to what? C of t is equal to Laplace inverse of C of s. First of all, find out C of s, then you can get C of t. So if you want to look at the other options, here are the options. C and D are the options here, right? So you can just find it out from these only. U of t into 1 minus 3 exponential s, right? So in order to find out C of t, you have to find out C of s first. What is C of s? C of s is 1 minus 2s divided by s into 1 plus s, right? So the transfer function g of s is given as what? So here C of s is nothing but C of s is here R of s multiplied by g of s. G of s is equal to 1 minus 2s divided by 1 plus s. Therefore, C of s is equal to, what is R of s? R of s is 1 by s. Therefore, 1 minus 2s multiplied by 1 by s into 1 plus. This is C of s. So you have to split it using partial fractions. So using partial fractions, you will split it a by s plus b by s plus 1. A by s plus b by s plus 1. Find out a and b. If you find out, you will get a as 1, b as minus 3. A is 1 and b is minus 3. Right? Therefore, you are getting 1 by s minus 3 by s when it is 1 and minus 3. Right? So Laplace inverse of this is C of s, right? Laplace inverse of C of s. Laplace inverse of C of s is 1 minus 3 e power minus t. Yes or no? Did every one of you know Laplace transforms or not? आपको Laplace transforms, inverse Laplace transforms find out करना आता है कि नहीं आता है? Very good. So, is there any mistake in this? Is there any mistake in this? What should be there? Yes, very good. U of t. Since this is a causal system, you are giving input at t is equal to 0, output will be present only after t is equal to 0, not before t is equal to 0. Right? Right. So this is the output. You have to sketch it. So if at all you don't know how to plot this particular response, just see a simple thing. Just in all these cases, if you just know one simple thing, it will be very easy for you. That simple thing is, see, if you just put t is equal to 0, what is the initial value of the response? Tell me, what is the initial value of the response? Initial value of the response. So in the response, if you put t is equal to 0, C of t at t is equal to 0 is how much? Minus, that is 1 minus 3 into 1, that is equal to minus 2. C of t at t as t approaches infinity is how much? 1 minus, how much is this? As t approaches infinity, this becomes 0, therefore this is 1. Therefore the response starts at what place? The response starts at minus 1. Minus 2. The response starts at minus 2 and ends at what place? It ends at 1. So it will start at 2. It will exponentially grow towards minus 1. It will start at 2 and it will exponentially grow towards minus 1. This is the response. So out of all the options, which option matches this? Option A is the right answer for this particular question, right? So this is how you calculate the response of any particular system. Any particular system's response can be calculated in this particular way, right? So this was a very good question given in 2015. Is it fine? See, in this question, there is this might seem a little new to you, right? So see, what is omega? Omega is written as 2 pi f. Angular frequency omega is written as 2 pi f, right? The same way he has written 10 pi f, which means omega is equal to 10 pi f, right? So he has written 10 pi f means, see, one thing you can one thing you can do is you can separate omega from this. If you separate omega from this, what is omega? It is 5 into 2 pi f, right? This is equal to 5 omega, right? So in S is equal to sigma plus j omega, in S is equal to sigma plus j omega, here sigma is equal to 0. If sigma is equal to 0, only omega is present, right? So here also only omega is present. In the place of S, only omega is there. So if at all you want to write it in terms of S, if at all you want to write h of S, right? H of S is equal to what? It is 5 divided by 1 plus 5s. That's it. 5 divided by 1 plus 5s. So just calculate the unit step response for this. Unit step response for this. What are you getting? Yes, option B. Yes. Option B is 5 into 1 minus e power minus t by 5. So for unit step response, R of S is equal to 1 by S. Input is 1 by S. Then C of S will be is equal to what? C of S is equal to R of S multiplied by H of S. That is 5 by S into 1 plus 5S. 5 by S into 1 plus 5S. You can split this using partial fractions. A by S plus B by 1 plus 5s. B by 1 plus 5s. Tell me the values of A and B from this. Even if you want to convert this into pole zero form, you can do like that also. You can convert this into pole zero form also. You can convert this as, you take 5 common out of this. You will get 1 by S plus 1 by 5. Right? In this manner also you can do it. Right? So if you convert this in pole zero form, it is 1 by S plus 5. So that it will be easy for you to finding out this Laplace inverse. It is 1 by 5 plus S, right? So if you find out A and B, you will get A is equal to 1 and B is equal to minus 1 in this case. In the previous case, you will get B to be different. In this case, you will get B is equal to minus 1. So, sorry, not 1 and minus 1, A and B you will get 5 and minus 5, right? So in the previous case you will be getting different answer. And in the place of A and B you will be getting different answer, right? So Shubham Goyal, I will tell you how sigma is 0, right? So see here, if you just want to simplify this, if you just want to find out Laplace inverse of C of S, what you will get? It is simply 5 into 1 minus e power minus t by 5, right? This multiplied by u of t. Therefore, option B is the correct answer for this question, right? Option B is right. If we have S is equal to 1 plus j, right? You have to compare this with sigma plus j omega. You will say sigma is equal to 1, omega is equal to 1, right? If we have S is equal to 0 plus j, now you will compare this with sigma plus j omega. You will say sigma is equal to 0, omega is equal to 1, right? Similarly, if you have S is equal to 2 plus j 0, you will compare this with sigma plus j omega. You will say sigma is equal to 2 and omega is equal to 0. The same way, we have been given frequency here. What is the frequency? Frequency is given to be 5 times of omega. What is omega? Omega is equal to 2 pi f, right? So this is given to be 5 omega, which means sigma was 0 in this, sigma is equal to 0 in this. That is the reason why we have only omega, no sigma. Sigma is not present. Is it clear?